maybe take stock of exactly where we are. We started off the class, by the way, with this figure here running. And so now we probably understand a fair bit about this, right? We know what NAPLs are, both dense and light, and that they might behave slightly differently, although there's nothing very much that we've done to make the distinction between light and dense. We know that they might behave differently in porous media than they would in fractured media. We know that the denser ones they'll all sink, but the denser ones will sink below fluids which are less dense than them, such as water. And they will travel at some rate, which we now know is kind of controlled by relative permeabilities and permeabilities. And that they will get to some kind of equilibrium saturation that we can also rationalize based on capillary pressure arguments, which we've kind of done. So that's covers what we've talked about that. We know that we can look at that in terms of fractured media as well. And that fractured media are interesting because the conduits that they travel on are much more open than the grains, pore diameters or pore throat diameters within porous media. And so they can act as what we might think are superhighways, both being able to get into the subsurface much more easily because of the large apertures which might exist in fractures, and that they can also travel perhaps quickly because the permeabilities of these are controlled by the aperture squared, we found out, just based on fluid mechanics arguments. So we know a fair bit about these materials. So what we'll talk about today is trying to rationalize exactly what they might do in a practical sense from what we know about these behaviors already. So that's kind of our job for today. And so I didn't want to start with that. I will show this. So in what we'll talk about today, this is the material we'll talk about, 2.6. Guess I can do that, and I can do that. And so we've kind of begun the recap, but kind of a recap from 30,000 feet. And so we'll do something a bit more detail. And we'll talk about the movements of non-aqueous phase liquids, both for lighter than water and denser than water, in terms of what the saturation profiles we expect to look like, based on what we know now about capillary pressure versus saturation diagrams, and also say something about what the thickness of the floating products might be, for instance, when we look at site investigation in these systems. So, the second recap then, I suppose it's probably easy just to come back to this. This actually embodies everything we've talked about so far. Thank you. And that is that the rates at which the distribution of fluids as they go in the subsurface in the first couple of months is controlled by this diagram on the top, capillary pressure versus saturation diagram. We know it's hysteretic. We know some of the ordinates on this are the bubbling pressures, where a non-wetting fluid breaks in as a bubble into the system and then displaces water back towards reduced saturation. As we increase the pressures between the two phases, we climb on this graph and get a larger saturation of the invading NAPL, which I guess would be this amount here, at the expense of the receding wetting phase, which would be water. If we come back down here, we go on scanning curves or we change, and either ways we end up with these other two important features, which is an irreducible saturation of the wetting fluid and an irreducible saturation of the non-wetting fluid. This is the maximum amount of the oil that we can get out of the aquifer as we invade it with water, and this is the maximum amount of water that's left in the aquifer as we invade with the non-wetting fluid. We can also define the rates at which things move in terms of permeability. Permeability defines the rate at which fluid moves in the subsurface. It's the same for a porous medium or a medium, irrespective of the fluid that's in there. And the only thing that defines the permeability relative to that phase is what we've called relative permeability, which is shown here. And we can define those behaviors based on these graphs. They could be X graphs. They could be X graphs with the tops truncated for good reasons that we've talked about, because of these inadmissible areas on the ends of the distributions. And they have certain features. They're curved, they're hysteretic, not shown here, just like these and for the same arguments. And the non-wetting relative permeabilities climb higher than the wetting permeabilities at the maximum magnitudes at the irreducible saturations, because this occupies the biggest pore throats first. And ultimately they have to go up to this location here. When it's 100% saturated with water, you'd expect the relative permeability to water to be 100% and the relative permeability to the other phase to be 0%. We can have capillary relationships that describe both this bubbling pressure and the permeability. And so we can use those to say something about a relationship between bubbling pressures and permeabilities from those relations, which tells us why this 0.3 Leverett J function, 0.4, is the way it is right here. And so we've covered a fair bit of ground, and hopefully it should be rational as to what we've done. And so now perhaps we can use this information to say something in a practical sense about how we might deal with regions contaminated with these fluids, and so understand something about it. So that's kind of a summary of what we've talked about so far. So I will move back here. Happy to take questions if there are any. But so let's talk in a practical sense about their migration. So movement of these things in the subsurface. I'm using my blunt instrument here. And first of all, lighter than water, and then denser than water. And so I won't use portions of these notes, which I think now are irrelevant, but I will go back to this slide. You've seen this multiple times. I'm not sure if you're using your notes, but I just kind of copied it, and I'll clean it, actually. So I'll get rid of all the garbage that's on here. If you want to get it before it's erased. There it is. So, don't you love technology? So this also epitomizes what we're doing in terms of the role of these capillary pressure versus saturation curves in defining behavior. We only talk about it in terms of wetting and non-wetting fluids. It could be that the wetting fluid is water and the non-wetting air, or it could be that the wetting is water and the non-wetting is a solvent. We can think of these capillary pressure versus saturation diagrams as defining the relative saturations of these components, and that as we go up within the column, this capillary pressure height will scale with elevation. And this would be the saturation of the non-wetting fluid, which is increasing with the difference in the capillary pressures, and the saturation of the wetting. Quite rational in terms of what these distributions would be. We can scale capillary pressure with elevation, because we know that the capillary pressures are really just the elevation of the unit weight of air minus the elevation of the unit weight of water. Would be another way to write this expression, right? Take the z's outside. And so it scales with this. And if we turn it upside down and flip it, then the same holds for the capillary pressure versus saturation curves, where this would be again, the saturation of the non-wetting fluid and the saturation of the water. And it changes from being 100% water saturated at this one with none of the other component there, to being a mixture. And of course they sum to unity because of those. So that's kind of the picture. So I won't belabor that because we've looked at that before. And so perhaps, maybe, we can make a connection between some of the things that we've seen, and we've used this curve a lot, in terms of this little cartoon, if you like, of the architecture of these puddles, these pools of NAPL in the subsurface, these chimneys of the non-wetting fluid as it's smeared, as it's come down through the column over some perhaps relatively short period of time, and to understand exactly how this relates to these capillary pressure curves. So that's going to be our main goal today. And so I will rely on the figures that we have in our notes to do that, which are taken out of Fetter. And so this is for the zone which is immediately above the water table. So this would be this case here, right, for the capillary, the behavior in the capillary fringe. We've made the case that it takes a certain bubbling pressure that we have to overcome before we can get a bubble of air in there. So I guess the capillary pressure for this particular component here would be what we've called PC0, or the bubbling pressure. And we could also say that that is equal to 0.3 is equal to the Leverett function. And you know this, right? And so this is probably what we wouldn't know. You might have a good idea of being able to get permeability from running an experiment. This is actually porosity on the bottom. And this is interfacial tension of the water in air on the solid substrate. And so up to this point, there would be no air in the system because it's the so-called tension saturated zone or capillary fringe. Above this, then we have the funicular zone. This would be the saturation of the non-wetting fluid, which would be air. And this would be the saturation of the wetting fluid. We also know, I guess, something about these geometries. So if this is a porous medium, and I can be very fancy here. I can be fancy. Such skill. So I'm not sure what we've done. Maybe we use blue for the wetting fluid. So in this case, I guess this would be fully saturated with water. At this stage here, it'd be fully saturated with water, and a small amount of, if I can draw it, I don't want to use this. This gray would be a bubble of water. No, sorry, a bubble of non-wetting air, not water. And this, as it's marked on here, is what we've called funicular saturation. Right? A funicular railway, cog railway up a mountainside, to get this bubble of water out of the pores, you have to carry it with the motion of the water. The only thing you'd suck out of it, if you sucked with a straw, would be the water. And so the water has to carry the bubble through these pores, and it's just not going to be able to exert enough drag force to be able to do that. And in the pendular zone, what we would have would be these menisci of water just around the grains. So the water wouldn't fill up the pore space. There would be these donuts around the grains, and the big bubble of air in the middle would be this whole region here. And so this would be pendular saturation of the water. W. And so that's kind of, from the logic of what we've talked about, that's exactly what we would think about. You could also think about these saturations existing, I suppose, on the landscape of this curve, right? So this would be according to the saturation according to this. This would be what we call funicular, and a saturation according to this. This would be our pendular saturations. So you could think of them as existing on this curve. The pendular one is higher in the column. Obviously this one is higher in the column. This one is lower in the column. And so hopefully this all kind of fits together. Yeah, so. Yeah, shout.
Is that sort of like relative to what you're defining? Like, it's like lower on the curve, could you say it's pendular saturation of the water?
Well, it will only, well, pendular saturation specifically refers to the fact that these, I don't know if they're, I don't know what the Greek, it must be either Greek or Latin. What does pendular mean? Pendant, hanging on? Clinging? Yeah, yeah. I think it'd be clinging, hanging. So the non-wetting fluid will never be in contact directly with the grains because it's hydrophobic. It's phobic to the grains. It's not hydrophobic. So the pendular saturation will always be at the grain boundaries, and the funicular one will be opposite. If you switch the wetting so that it's oil wet instead of water wet, then the fluids will be reversed. So it'll be the DNAPL which is attached to the pendular rings. Right? So I don't know if I answered the question.
Yeah, that kind of helps. Yeah.
Close enough. Good. So that kind of governs exactly what we're talking about. So if you look again at the unsaturated zone, and these are in your notes also, we can look at the incursion, if you like, which again follows this, of a non-wetting fluid. So in this case, this is a snapshot between time 0, and these are actually experimental measurements. I think, well, probably in the lab. A 60 centimeter column is a 0.6 of a meter, so a couple of feet. After 480 minutes, so that's 8 hours, is it? And final conditions. So initially, you see exactly the column that we had here for the vadose zone. It would comprise the same things. But now we're introducing a third phase. And the third phase is this oil. And so we can think about this in terms of this. This is in water content. So you'll remember that water contents are this agricultural engineering or agronomy term, which is the volume of the phase divided by the volume of the voids. Porosity is the volume of the voids relative to the total volume of the porous medium. And saturation is equal to the volume of the phase divided by the volume of the voids. So, just in case. So in other words, we know that this, if this was written in terms of saturation, then this would be 0 saturation, this would be 1 between those. So they just vary. So the other thing we also know, I guess, is that this maximum volumetric moisture content, if we could get to this point, would be the same as the porosity. In other words, when all the voids are filled, then this would be V alpha, and these two would be the same as each other. So the maximum water content is equal to the porosity. But never mind, we digress. So if you look at drawing this invasion of this tongue, which is attempting to move downwards, right? This is being injected. So this would be the volumetric moisture content of the air. This would be the volumetric moisture content of the non-wetting fluid. And if I blow this up, this would be the volumetric moisture content of the water. And so I suppose we could also write, it's easier to write that the saturation of water plus the saturation of air plus the saturation of the non-wetting fluid, which is oil, this other non-wetting fluid, is equal to 1. And I suppose if we wrote the volumetric water content plus the volumetric air content plus the volumetric non-wetting content, what's that equal to? think, right? Just because of this. And below this, if we draw a line across, the other phase hasn't reached it, so we're only adding two together. This is a saturation of water, saturation of air for these two. And those two add to unity. If you allow it to continue, then you see that it travels further downwards. So that this now completely would be divided into the three components. So air, non-wetting, and wetting for each of these. And also down here, if we drew a line across, it wouldn't be so different. These would be the relative volumetric moisture contents. And I guess what is interesting to note is that this length here is widening compared to this. And it's widening because, as you'd expect, it's being buoyed by the water table. So by definition, we could think of this is the top of this is the tension saturated zone. And we also know, the one thing that we know by definition is that the pressure at this point here is equal to atmospheric. And so if we're using gauge pressure, that means 0 kPa, right? 0. And so this is in tension, hence the tension saturated zone. So the pressure here in the water would be less than atmospheric, according to the height multiplied by the unit weight of water, which we'll talk about a little later. And so this represents kind of the tension saturated zone. So it's mainly saturated with water, but of course there is a little bit of air in here, right? And a lot of water. And so what you can imagine happening is that it squeezes a little bit of this portion down as the weight of this adds on top of it, and it compresses it. Because it's, instead of just having a column of air above it, so right here, the only thing that exists above this particular point here, from this point upwards, is just air, which has 1 kilogram per cubic meter. Water below it has 1,000 kilograms per cubic meter. And if this is an LNAPL, perhaps that has 700 kilograms per cubic meter. I'm not sure what the density of gas is, but it's of that order. And as time keeps on going, then I guess the most telling one of these is this one. So this is perhaps the key one in terms of our understanding. So if I take a line that goes across here and draw separately between them, then this represents the effective saturation of the non-wetting fluid, or volumetric moisture content. This represents air. And remember, we're referring to this point here. Perhaps do it down here. This represents water. And it doesn't take too much of a stretch of the imagination, I guess, to flick back to these cartoons and to think that that's exactly what these are, right? So this portion here, this happens to be a DNAPL, so perhaps we go back to this one here. So as you go down through some kind of column, you could imagine you could have some zone of smear. This is a pool of gasoline. It's lighter than water. This is the water table identified here. And so there's no reason that it's able to get below the water table because it's lighter than water. It's the salad dressing shaker. and so it sits on there. What it will do is that instead of, at this point here, the weight of the fluids above it acting on the water table, the fluids above it are just air. So it does have a weight, but not very much. This now has 500 kilograms per cubic meter, and so it's going to push down the water and depress it. Maybe there's a pool that gets to the water table as well, but this distribution of a chimney, which is not shown in great detail here, but perhaps I can use this. This chimney, which is present at kind of residual saturation as you go down here, is reminiscent, I think, I hope, of what we just talked about in terms of this figure here. So that's exactly this. Going down through here, there's a saturation of the non-wetting fluid. I don't know, is this 10% saturation? The saturation of water is 2%? 3%? I don't know, I'm just guessing. And the saturation of air at this point oh, sorry, not that one. This one here. I don't know. I guess it would be 87%, right? If we're sticking with these numbers. 310 and 87. And so this, in this zone here, there's a chimney. It's mainly air. There's residual water stuck in there. There's residual NAPL stuck in there. If you wanted to remediate it, the one connected phase you'd be able to push through there would be air. So you could use hot air to vaporize it. Air sparging or something like that. That would make sense. Once you get below this, you have this pool of almost 100% NAPL, not really 100%, but what is it? This saturation is 60%, probably 70%. This one here. This is 15%, and this is it's less than 15%, but to add up, they have to add up. So 15 plus 70 plus 15 is indeed 100. And it mimics exactly what we have. We have a lens. And so this also kind of informs what we might want to do. So to take this out, we might want to get rid of the free product. It would be very easy. If you stick a straw in this, everything's connected and to NAPL. And so as you suck it, you'll suck NAPL. You won't be able to dislodge the water because it's held as a pendant saturation. And you won't pull air out of it either. But you will be able to pull out NAPL. If you pull the NAPL out, you'd reduce this saturation in the middle, perhaps at the expense of water coming back into it and or air. And at some stage, the NAPL would snap off and it would be present only as bubbles, funicular saturation that then you couldn't get out. And so just from looking at this interpretation of our capillary pressure versus saturation curve, which is saturation versus pressure, this is saturation versus elevation, but they connect to each other through what we talked about on this diagram here. Then we can say something about what they look like in situ. So it explains exactly what our puddles of these things are. The other thing that, and we'll go back to that, I guess the important thing is to realize that potentially we have what you think of if we have a water table, which is where the water is at atmospheric pressure, where it's fully saturated. You could almost think of this as an oil table, where somewhere within this portion, at the top of this, the pressure on the top of this plume is also at atmospheric pressure because it connects with the atmosphere above it. And so we'll maybe talk about that. Oh, we'll talk about it now, actually, I guess. I'll skip that. So if we, instead of looking at those figures, if we imagine exactly the same experiment, I don't think it is the same experiment, but if we imagine exactly the same thought experiment, this one now goes from A to B to C to D, so instead of, goes in a different order. So you do the same thing. This is what our pristine porous medium looks like. This is where the water table is. This is atmospheric pressure, which is 0 gauge. This is a tension saturated zone, which is still almost fully saturated with water. So this is this point here, where even though it's at negative pressure, the negative pressure isn't enough to allow a bubble of air to poke into it. And so that's what this portion here is, capillary fringe. And all the way up here, the pressure is decreasing because if you look at, if I use green, if you looked at the change in pressure in the air, this is the pressure in the air is equal to elevation multiplied by the unit weight of the air, right? And so by definition, this difference in these two pressures is our capillary pressure. So that's what this difference is here. The water pressure is negative. Negative centimeters of water. The air pressure relative to this point is negative. It's decreasing as you go up. It's not actually negative, but it would be relative to gauge pressures at this point. And so this represents a positive value of capillary pressure. And of course, the extension of this is just a straight line, that as you go down below the water table, the pressure builds as pressure of water is equal to Z gamma W. And I suppose this would be negative, right? This is negative Z as we define it. We'd use our fluid mechanics sign convention. So below the water table, this is negative Z. And above the water table, this is positive Z. Doesn't matter. You just need to use your intuition about what these would be. So now, into this, we enter this gasoline, spilling it from the surface. So now, the distribution of pressures changes like this. You now have this nose of the saturating fluid as it comes down. Dancing kittens. And as you get this nose coming down, further compressing it, the water table, instead of being here, has risen to this point because it's being compressed by this gasoline on top of it. As it keeps on moving down, the pressures change. The water table actually rises from its initial point, which was equal to 55 centimeters, which would have been down here and down here. And you see these two different systems. And so this would be oil. This would be water. It's already got this little triangle on it. So this would be water from here on downwards. This would be atmosphere. So above this point here, if we use a different color still, this would be air. So you have the three phases. You have, if you go down vertically, you go down to the top of the oil table here, which is this green. This would be the oil table existing below here. There's a portion of here which seems to have a negative pressure, which you might think would have air in it that hasn't been squeezed out. This portion here. And then below here, you'd have water. Yep?
So would there be like a water table, an oil table, and an air table per se?
Yeah, I'm not sure it's an air table because it has a cushion. It's an air cushion. It's
Okay.
under pressure. It's being pressurized from the top by the gasoline that's sitting on top of it,
Mhm.
and so yeah.
That makes sense.
It's not a water table, I guess, officially, right? Because it doesn't necessarily have zero pressure. The definition of a water table is atmospheric pressure.
Okay.
And so this has atmospheric pressure at the oil table. This has atmospheric pressure, surprisingly, at the water table. And between these, there's this kind of non-defined, nondescript region. So, yeah.
That makes sense.
So-
Thank you.
Yeah, I think probably not calling it an oil. So this, and then finally, this would be the water table. This would be the oil table, because both of these intersect this pressure at this point here. And we'd have this. And so the ramifications, I guess the significance of that is that if you think about this structure where you have supernatant oil overlying an air cushion and overlying water, is that if you go in and try and sample it, then you have to rationalize exactly what it is you're measuring in the field. And so, you know, one of your entry-level jobs, in fact, some of you might have done it already, would be to go and work on a drill rig and take samples. And so if you look at the one way that you'd be able to get access to the stuff and to be able to know what the depths of these different fluids would be is to put a drill hole down and put a well down that would define that behavior in the subsurface. And so this would be the drill hole that you'd put down. And this would be our system of LNAPL. And the green would be our oil sitting on top of the air cushion, which is the gap here, and the water underneath it. As the oil flows into the wellbore, because it won't see capillary pressure in the wellbore, it only sees capillary effects in the fine-grained medium it's flowing out of, it can go everywhere in the wellbore it wants to. And so the thickness that you'd see in a wellbore is actually a false thickness of what exists in situ. So that's, I guess, the main question. And you can rationalize that by thinking about what we just said about the oil table and the water table. And so this here is going to have a pressure of atmospheric. This here is also going to have a pressure that is atmospheric. This is the air cushion between it. And what we could do is we could look at the pressures that are acting at this little oil-water interface within the borehole. And all we need to do is to take this out and do a free body diagram that allows us to make sure that the pressures between these two fluids are the same. If they're not the same, then it's an interface which is moving. If they're the same, then F equals ma, there's no acceleration. So the pressure acting down is going to be the height of the fluid in the wellbore, T, multiplied by its unit weight, which is this. This is acting down on the column of the fluid in the wellbore. The pressure opposing that, acting upwards, is the pressure in the water acting upwards. And so the way for us to get that is to go from this point here, whoops, and go into the wellbore like this. We know these 2 points are simply connected. We know that this point is atmospheric pressure. And so if we wanted to figure out the water at the base of it, it's going to be equal to this pressure here, which is going to be equal to pressure is equal to the weight of water multiplied by the depth times G, or the weight of water multiplied by this. And we can equate them to each other. So if we equate these to each other and we solve for the term we don't know, the ratio we don't know are the ratio of these heights. And so this is what we measure in the wellbore. This is our density of oil, I don't know, 500, 700 kilograms per cubic meter. This is density of water, so maybe this is 0.7 times T. Just this. And so if we have a way of being able to measure this thickness, we're automatically able to say something about the thickness of this lens that's sitting within our porous medium, which we've just pierced with our borehole. And by piercing it with the borehole, we've made the reading of the depth inconclusive, I guess. And so our way then to use this is to take our assembled knowledge of everything we've looked at so far and think about this being the real profile that we have in terms of these complex distributions of some water, lots of air, and a smear of oil in this chimney as we go down. Once we get below the chimney, we're sitting in this puddle of non-aqueous phase liquid, and that puddle is on top of some water and some air that's trapped above it before we go into fully water below this zone. And so what we could do is try and simplify this by just saying that maybe if this is the true thickness of our lens, which we've called W, then we can calculate the amount of NAPL that we have in the system just by drawing it out. And so I'm just going to draw out our puddle in 3D. So it's going to be our prismatic lens that we have on top of here. So all I'm doing is drawing a prismatic lens that looks like this. And it would be described by an area. It would be described by a real thickness, not the thickness we measure in the borehole, but a real thickness. Okay, yeah, all right. So, yeah, fine. So this would not be that, right? This would be how would you do it? This is T. This is W. So this is T minus W. Right? T minus W is this length here. And it's multiplied by, so this together here is a volume. This volume multiplied by porosity would be the void volume. And the portion of the void volume that's taken up by this is 100% of the void volume minus the irreducible saturation of water. How much water is in the system? In other words, this amount here. And SW air. So this is SW0. Is this? And this is air. Irreducible saturation of air. And so the difference between these, no, incorrect, that's not right. So 1 is this full width, right? Subtracted by this amount and subtracted by this amount. So in other words, this amount here in the middle is equal to the bracketed term here. And so if we know what the area of this pool is, if we do know it, not a very easy thing to find out, then we're able to say what the volume of product would be in our system that we have to remove. So simple mass balance calculation. We made this problem kind of simple, or we reduced it maybe to its principal components. These graphs that we talked about are all relate to the capillary pressure versus saturation curves. So if we wanted to do something much more complicated, which we won't do, we could imagine taking the capillary pressure versus saturation curves that we developed before. Remember, we used this Brooks-Corey idea that we could take logs of the pressures and logs of the saturations, effective saturations, and reduce these curves to straight lines in log-log space. And then they define the bubbling pressure and the distribution of the saturations. We could do it for air and the gasoline, and we could do it for the gasoline and water, and we could combine those to be able to reconstitute these capillary pressure curves top and bottom of the column. Instead of doing them as curved curves, we could use these relationships as straight lines to get some equations for it. I'm not going to make us wade through this. You see these derivations which are in Fedor. But if you do that, you basically end up being able to rationalize some equations that would basically tell you what we just set up here, but after 4 pages of derivations. So we won't do that. But this is a good way to be able to get a ballpark of what the saturations would be. The main deal is to realize that the depth of product you measure in situ is not the true depth of product you'd have because of this air cushion and oil table effect that we just talked about. Okay? So if you have Fedor, you can look at Fedor to get that. Who has Fedor, by the way? Do many of you? Any of you? No? Fine. It's a good book if this ends up being your career. But you'll have more money in the future because people will be paying you to give them wisdom than receive wisdom, in theory. So following on from this, I guess this is just an exposition of what you could imagine would happen in terms of smearing of LNAPLs again. If you get gasoline sitting on top of the water table, if the water table has an inclination to it, it will tend to spread laterally. If it spreads, then you could imagine that this would be the distribution of the different phases. Take any particular height that you want, and it would say something about it. And I guess here you'd expect this to be the lens, right? So this would be some air within it, but mainly the non-aqueous fluid, water and the oil at some concentration. This is at residual saturation. If the water table drops, then it would take this lens down with it. As it takes it down with it, because it's a relatively high saturation, it would smear it. Once it's smeared it, maybe it can move further. If the water table rises again because of seasonal fluctuations in the water table, then it would smear a portion of the oil at residual saturations. And so I guess the ultimate response, if you look at the non-wetting fluid, you'd have a chimney here which has residual saturations, which would be this amount here. You'd have a lens sitting on top of it, which would be at relatively high saturations, 50 or 60%, so it's all connected within the porosity. And then you'd have another residual zone, which is oil sitting inside water. The other fluid is water, which is then smeared through here. And so now, I guess the ramifications for what we know with Darcy's law is if you have a gradient of flow here, and here you do have a gradient of head, right? dH dx. You can imagine from Darcy's law that you get minus K over rho G dH dx. So the velocity, this is hydraulic conductivity, density of the water, gravity. This would be, no, you don't need that, forget that. This is hydraulic conductivity, dH dx. This is velocity. So you know at which velocity this travels. If you know velocity, you know that volumetric flow rate is equal to Darcy velocity times an area. So the area, I suppose, you could think of as being this cross-sectional area here. And if you have this flow occurring, then you know the mass rate of dissolved gasoline that you're moving is going to be equal to the volumetric rate of flow of water multiplied by the concentration of gasoline. Concentration that's dissolved in water. So it might be 1,000 parts per million, typically at very low concentrations. But immediately it allows you to calculate the rate at which the dissolved, certainly you can calculate the rate of flow just given by the inclination of the water table. And you can also calculate the rate at which fluids dissolved in water and carried with the water are transported horizontally along with it. And so there'd be different transport mechanisms in the air. If you pump air through the vadose zone, you'd be able to vaporize gasoline within this column. If you used hot air, you'd be able to vaporize even more of it. And in the water table, if you sucked through a well water out of this saturated zone, you'd remove dissolved gasoline at this proportional to the rate at which you can pump the water. And you know the rate at which you can pump the water because you know that Q is equal to area, relative permeability of water, permeability, viscosity of water, change in pressure gradient. I wrote it in head here just because physically the inclination of the water table represents that. You could calculate what the pressure gradient is from the head. P is just equal to gamma water H, right? So you know that. So that's it. So easy back of the envelope calculations that you could do based on what we've talked about today. So I think that's probably it for LNAPLs. So that's the reason that we're talking about this, to understand exactly why the architecture of what they look like as puddles and chimneys below chimneys look like they would be. Rationalize it based on our capillary pressure versus saturation curves, and also say something about the rates at which components move. This is the rate at which water is moving, by the way, in this, because water is the agent that's carrying the dissolved components. If you suck at a pressure across it and there's residual NAPL in there, none of that will come out. None of it will come out at all. So that leaves us to talk about DNAPLs. We have the same capillary pressure relationships that we know. But if now we look at denser than water fluids, we can use the same capillary arguments that we talked about. So I guess we're moving from being this capillary pressure curve which was above the water table here to one that looks like this, to be able to say something about how denser than water fluids will travel. We know the capillary pressures are given by the difference in the pressures. We flip the diagram upside down, and we should be able to say something again about the behaviors. We don't have this air table or air cushion that we've talked about now, because that's not part of our geometry. So we have to talk again about what happens if we drill a borehole through this system. And the first curve, if I get to it, is saying exactly that. So this is what we expect to happen. So you have a column that's had DNAPLs dropped in it. We know that as you drop it in, the only thing that stops it from moving is going to be an aquitard. So we know the only reason for DNAPL to stop is to reach something where the capillary entry pressures in the porous medium underneath it are small enough that it gets stopped. We know that if we have a ganglion that's long enough, it will keep on going as long as it doesn't neck down and disconnect itself. And so we could imagine what the distribution would be if, for instance, we drilled a borehole down through here. And so I suppose you could imagine that if you drilled a borehole through here and looked at the distribution of fluid sitting in the borehole, it won't just sit as a component that's floating on top of the water here, because there's nothing to stop it going down to the bottom of the borehole. And so you could imagine that if you drilled a well bore through this, it would saturate it all the way to the bottom of the well bore, because this would just empty into the well bore. And so that's the reality of what we'd expect to find in a system like this. So if your well bore is just this deep, then the DNAPL will fill it up and you'll get an apparent height, which is this. But if you keep on drilling, the height of the NAPL that you'll see appears to get longer just because you've got a deeper hole. And all it's responding to is the fact that the free surface for this wants to be here, and as long as there's enough volume in here to flow into here, it'll just keep on going down as long as you drill the hole. And so that's our mindset that we have to understand for this. We can think about the same capillary pressure versus saturation curves as you go down here, and they kind of describe the different zones that you'd expect to see. In the upper region, we'd have mainly air. The NAPL, so the zone which is NAPL, I will fill in as this. I guess I could have used some other blunt instrument. This will be, I guess it doesn't stay that way all the way down, right? Yeah, actually. This will be present as water, always. Oh, I'm getting, and I could use different. Yeah, so I guess that's a messy diagram, but maybe it gets the point across. Is that in the upper portion, it's mainly air-filled. It's left a smear of the NAPL as part of a chimney as it goes down. It's hit the water table, doesn't care about the water table because it's denser than water, and it keeps on going. And so it's taken this smear down through the water-saturated zone and displaced water. And then ultimately, as the pressure, capillary pressures have increased enough, so as you go further down from atmospheric pressure here, the column of NAPL here competing with the column of water, the capillary pressures have been increasing, and therefore the saturation grows. Because if you look at this capillary pressure diagram, right at the beginning of what we talked about. This represents a larger capillary pressure. I know it's for the vadose zone, but this capillary pressure here is the same as this. So a larger capillary pressure differential gives you a larger saturation of the non-wetting fluid. And you end up with some kind of distribution that I guess I didn't talk about here, but I did talk about here. And it explains exactly what we think. This represents a pool that's sitting on the bottom of an aquiclude. So there must be something on the bottom that's sitting here. If we drill a hole, it keeps on going down to the center of the earth. This will extend all the way to the center of the earth, so long as there's enough volume in this region to pour into the borehole and top it up. So this is the lens at almost 90% saturated DNAPL. As you go up within this, this is more water and less DNAPL, and above a certain zone, the smear is through a zone which is part water and mainly air in the upper chimney. Again, if we blow hot air through this zone, we'll vaporize the NAPL. If we blow water through this zone, we'll dissolve the NAPL and take it out. If we blow liquid through here, we'll move free product only that will recover, and the water will be immobile. And we can rationalize all those mechanisms based on what we know about capillary pressure diagrams, the form of the saturation, and our knowledge of relative permeabilities, I suppose. So the final thing to talk about, almost the final thing, is that we'd also expect these distributions to be a bit different based on how we think the porosity or permeability would change in the subsurface. So if we have an aquifer which has a high permeability versus an aquifer with a low permeability, the distribution of saturations that we'd expect to get would be less, because it would compress the capillary pressure versus saturation curve, right? Remember, if I draw this curve as upside down, it's below here. We know that this bubbling pressure here versus saturation. We know that this bubbling pressure represents the first bubble of air or NAPL that gets into the system. If it happens to be a very open system, then this bubbling pressure will be at very low pressures because it's very open. And so this entry pressure into this would be quite high in the spectrum. If it's very tight, very closed, the capillary pressure that we have to overcome to get to this bubbling pressure is much larger, and that would be much deeper. So we'd expect that if we try and translate these capillary pressure curves onto this template, if it's high permeability, it would be kind of squashed upwards, and if it's low permeability, it would be stretched downwards. And then that really speaks to us in terms of what we expect the saturations to be. So in other words, for the high permeability material, below this point, we'd expect it to be very high saturations of oil. But in the low permeability stuff, this would still mainly be water. In the low permeability material, now this would be oil. This would be water. And this would be air. And I could write those up here as well. So obviously for this low permeability one, this would be H2O. And yeah, I won't draw the other one. And so if I draw the saturations for the low permeability at this height, the saturation of the low permeability one would be H2O. And air. Air is mainly nitrogen, right? Not oxygen. And so if at this height here, in the low permeability material, it'd be mainly water, and there'd be still just a chimney of residual fluid. But in the high permeability stuff, tons of oil would have gone down here already and be kept here at relatively high saturations, and it would have squeezed out much of the water because they can't both coexist. Conversely, as we go down to deeper depths in the low permeability one, there'll be now a large saturation of oil and a smaller saturation of water. And I suppose if I did this for the high permeability one, this would be H2O. And this would be oil, for want of a better term, right? So we could contrast the things. So it explains why the distributions of these things look like a chimney in air, a chimney in water, and then a puddle sitting at the bottom of somewhere where it can't go anywhere. And it can't go anywhere only because there's an aquitard or aquiclude, which is excluding it from going below that region. A capillary barrier, I guess we'd call it. And the rest, I guess maybe we have a few closing remarks. The main closing remarks, I guess, deal with sampling. And so this, I suppose, explains that exactly, right? If you drill a borehole, and that borehole goes through a pool of LNAPL sitting on the water table, then what it would give you would be this height of NAPL that would sit on top of the water in the borehole, but this wouldn't represent necessarily a true depth. This, in our borehole, as we said earlier, this would be height T, uppercase T. And actually we want to be able to determine what W is, right? We just talked about that. And so if we drill a borehole through a gasoline contaminated site, we'd sample this height and we'd measure T, but we want to convert for what the real depth is. And if we know what that real depth is, we can convert it into a mass that's present in situ from the calculation we just did. If we drill the borehole through a DNAPL contaminated site, the deeper we drill the borehole, that borehole will just keep on filling with the DNAPL. If we drill the borehole deeper, so long as there's a supply, it will keep on filling up. So the only thing that's relevant to us is the upper reaches of this, which will represent a portion on the capillary pressure curve where it saturates to one of these high magnitudes. So that's what that point there represents. And so when we go in and do our sampling, it matters what we're going into and how we sample it. We'd like to be able to measure this depth, and we'll talk about this just maybe to close out how we might do that. And if we want to measure the depth within the DNAPL, all that matters is the absolute height to which it rises, not the depth to which it goes. I suppose in addition to this, we'd want to know where the maximum depth of the capillary barrier was. So if this is the upper region of our capillary barrier, we would know that the true depth of our DNAPL would be equal to this height here, right? This is what we've called W before, kind of, right? The true height? Perhaps not that, true height. And so we need to be aware of this. The other thing is if we sampled this with a baler, a tube that has an open top, we'd want it to go down, sink below this top, so it would decant into the baler. The other thing we could use is a baler that has a valve at the bottom, typically just a ball bearing, that rises as the pressure pushes up against it, and it flows into the baler from the bottom, and then we can sample from up here. And so the whole thing about sampling of these well bores might be something we would be interested in trying to do. And so that was what the other figures were that I put here. So, from someone's Facebook page, Julie Reich, whoever she may be.
This looks familiar.
You've seen this before?
No.
She's a friend?
Water sampling.
Yeah, fine.
This looks familiar because I've done water sampling before.
Yeah, fine. So that's exactly it. All right. So, just for boreholes that are filled with water, you drill a hole. You can drop something down until you hit water, and typically what you drop down would be this probe, and all it is two conductor wires with a weight on it. The conductor wires are present within that weight, and then when the conductors hit a water surface, they make a circuit and a light comes onto the surface.
And then you record it in your phone or whatever data you have.
Yeah,
So apparently there are ones that you can put on for higher wells that you have to stand to get it, and there's ways you can put it on your leg and stuff. There's different positions from what I've learned. But it is still a pain in the ass to crank it all the way up.
Oh, no swearing, please. So yeah, it's fine. I don't care.
We did this all summer in giant monitoring wells. And on top of that, having to be on the watch for black widows. It was tame.
Well, yes, okay, perhaps there are spiders and things. Black widows, you don't get black widows in this country?
I was in Arizona. There's black widows in
Oh,
the
yeah,
desert.
fine. Yeah, that's right. So, all right, so that's the first deal of this. So you can imagine that you can solve that. Don't be packing up yet. We've got some more videos to watch. Come on. We're just having fun. So you can get the depth from that because the lead is calibrated in terms of feet. And so that would be another junior level job for you to do.
So I had one like noticed like that. There was like two different kinds of those that I worked with. One that was more like the one in the video, and then one that was just like they have one inner wells, and I had to get used to cranking, pulling up hundreds of feet of cord over the summer to get my.
That sounds like a baler.
Well, I got really good at it by the end of the summer. I was able to
This is a short description of the LNAPL flute system developed by Flexible Liner Underground Technology.
Yeah.
Oh yeah. That's
So the other part of the story is, of course, if you have gasoline sitting on top of water, then you might want to measure the top of the gasoline. And so the other way to do this is to, I think you can get sticks that, the same as when you see the Sheets truck pull up to the gas station. They have a big long stick that they put into the gasoline tank to be able to measure the depth of it. So that you could use the same thing here. Have some substance on the stick that reacts to gasoline relative to air and marks the level, or reacts to gasoline and not to water. And so this is the same idea as this. You have some kind of fabric that you put underground, you put it along the length of the borehole, you withdraw the sleeve around the borehole so that a portion of this fabric becomes smeared with the stuff that's around it, and then you measure the system that goes in. So I guess this is trying to explain it. So you drill a borehole, you put down a composite tube on the outside, but with the cloth on the inside down to the bottom. You retract the covering sheath around the fabric tooth up to the surface, and then it sees whatever is in the aquifer around it, and then you pull out the whole fabric sheath and you measure what's there. And so you get a picture of what's green, what's blue water, and in DNAPL what would sit at the bottom in the sump of your hole. So you're able to do those. And of course now you know exactly why you do that, because you have an oil table, an air cushion, a water table underneath, and that the DNAPL will just keep on going down, and it's only the top of the DNAPL that's of relevance in what you deal with.